Good morning, everyone. Nice to see you. Just thought I'd check in to see how you're all getting on. I'm going to go through the rates of reaction work that I recently set, but I'm going to talk you through the whole thing. But I just wanted to say thanks for everyone who's given in the work. Thanks for working hard. And also, just so you know, this is the fourth time we're doing this video because our camera skills haven't been great. But I'm going to say this again. Thanks to our cameraman. If you fail this time, there will be consequences. Okay? Alright, so, ready? I'm just going to talk you through very, very quickly the whole sheet, and feel free, please send me any questions you have. Some of the work has been brilliant. Well, actually, everyone who's given in work has been brilliant. So I hope we all get a bit more engagement. Although loads of you are doing it, and it's fantastic. So anyway, come back here, please, Em. So the first thing then, just to go on the sheet and just look at the sheet. I have started filling this in because, like I say, this is the fourth time we've done this video. No zoom in, Em. Remember? Okay. But I'm just going to talk you through it. So what is the rate of reaction? The rate of reaction is the time taken for products to form, or products to be made, or reactants to be used up. What is collision theory? Now, I've drawn two little balls there, colliding. And basically, collision theory states that for a chemical reaction to happen, these two particles have to collide with enough energy, okay? So collision theory is all about particles colliding with enough energy. And if they didn't have enough energy, what do you think might happen if they didn't have enough energy? Let's be a particle. Come on. What might happen?
I'll be the one without energy.
Okay. See? No reaction. So they've got to collide. Go back a bit. They've got to collide with enough energy. Boom! And that energy is called... What do we call a word that starts something? What's it called?
Piston?
No, not quite. Starts. Active.
Activity.
No, activation energy. Close. Okay, that'll do. Okay. So I'm going to run through these questions now. Reactions that have high energy, reactions that have reactions that happen slowly have a low rate of reaction, or slow rate of reaction. Reactions that happen quickly have a high rate, or they're fast. You know, the rate is high, I would say, or a fast rate, I suppose, as well. Okay, so just on the sheet for me, please. The chemical weathering of rocks is a slow reaction. I mean, it takes thousands of years, and explosions are very, very fast reactions. So we'd say, you know, they got high energy, but also they have a very high rate, or they're very fast. So the two ways of measuring the rate of reaction. You either measure the reactants being used up or measure the products being made. So for example, if I added magnesium to acid, the magnesium would disappear. So we'd measure the reactants being used up. Likewise, if I was making, I don't know, think of some food that we sometimes make. If I was making fish, I'd watch the batter kind of cook. That's a product being made. Make sense? And it's all about time. So the equation for measuring the rate of reaction. We can measure rate of reaction. You know, we can do things like the mass of a substance, the volume of gas, or even just visualizing. Now, if we were back in school, we'd be doing the disappearing cross experiment. I think actually we did do it before we left, where the cross disappears because there's a precipitate being formed. So there's loads of ways of measuring the rate of reaction. How do you measure your heart rate? What do you do?
Get a watch.
A watch, and then what?
Put on heart rate.
Yeah.
So it takes the energy from there, transports it to there, and then put it back.
Okay, but wouldn't you just be better to hold your heart, count to 10, and see how many beats you have in 10 seconds?
But then how do you know that you have it in 1 minute? Heartburn.
Well, you times it by 6, because how many times is there 10 seconds and 60 seconds?
There are 60.
Well,
1 minute. 1 minute.
1 minute. Right, carry on with this then. Okay, we're going to go through these questions very fast. I'm going to try and keep this video short and sweet.
Yeah, because it's already been 4 minutes.
Nobody wants to be talking to me for too long, do they? Right, so rate of reaction here, 24 centimeters cube hydrogen gas produced in 2 minutes. What is the rate? Now the rate is basically the amount of reactants used, or the amount of products made over time. So it's just a simple division. So what is the rate of reaction of 24 centimeter cube hydrogen gas produced in 4 minutes? Well, literally, it's 24 divided by 2 equals 12. 12 what? Well, for every minute, 12 centimeters cubed of gas are made. So you just write 12 centimeters cubed per minute. Next one was 11 centimeters cubed of CO2 per min. Okay, And what is the rate of reaction of 3.4 grams of copper sulfate produced in 4 days? So it's 3.4 divided by, 3 days, 3 equals 1.13 grams per day. Can you see each time I took the units from the equation? So if I give it me in days, I use days. If I give it me in minutes, I use minutes. Just keep it very, very simple. Drawing graphs. Now these are some fantastic graphs.
What happened?
I don't know what, you've done something. Please don't mess. I did say, didn't I? You've done something. You've done something with a colour. I don't want to stop this video.
Uh-oh.
Oh, there we go. Right.
No,
We're back. Right, keep it like that. Please don't press anything, okay, babe?
Okay.
Right. This will be the 6th time we have to do this video, otherwise. Right, anyway, we're still on. So drawing graphs. Volume of CO2. Graph. These are just graphs I want you to look at, actually, okay? And it shows that the reaction is always fastest at the start, because the curve is the steepest there. Now, why is the reaction the fastest at the start?
Oh, I don't know.
Concentration is always the highest.
Yeah.
Okay, it's got to be, hasn't it? You start off with A plus B, and they make AB.
Wait, Dad,
You've got loads of ABs at the
You've
time.
got a pause button on this thing.
No, don't. Just in case, if we have got a pause button, have we? Go on and
look,
try it.
see,
Go on and try it.
pause.
Try it. Okay, so we can pause if we need to now.
Oh, so...
No, and we're still
Dad,
recording. Okay, play. Right, so we've just discovered a pause button, so that could make life a lot easier. But we're going to do this quite quickly still anyway. Now, in terms of this, I think some of you didn't have the graph paper, which is absolutely fine. Some of you don't in your book, absolutely fine. I just want you to get engaged with it. You know, I'm not fussy at all. But you think about it, the graph. You know, I'm going to show you something now in a sec. Okay, you kind of want it to be time, and then what you measure. So we got loss of mass, and you should have something that looks a little bit like this. Okay, so loss of mass goes fast at first and then slows down until it becomes, now see where this is flatlined here? That is when the reaction has stopped. And this is the main bit of the video really. This is what I wanted to talk about. Some of you said, well, you know, if you had a higher temperature or greater surface area, the reaction goes faster. Yes, it does. But if you've still got the same amount of marble chips, such as 5 grams of marble chips, you just get to the end point faster. But you do not increase the amount of products. And that is a common mistake that we see at year 11 as well, okay? Which is, these coming up in year 11 and they're coming up pretty soon, okay?
For 8 minutes.
Right, let's get move on then. Okay, what is the effect of temperature on the rate of reaction? Increase in temperature increases rate because particles not only move faster, but when they collide, they have enough energy called the activation energy. Sketch a graph to show how the rate of reaction is affected by temperature. Okay, so what I would do here is something a bit like, you know, this could be a normal reaction, which would be mass of product, something like that, and then again time. This could be our normal temperature. Increase the temperature, I'll do a dash, you get a faster rate at the start. Okay, so you have cold and you'd have hot. Okay, why do vegetables last longer in the fridge?
Because when they're colder, like the time of them freezes.
Yeah, so time goes slower in the fridge, is that what you're saying?
Yeah.
Okay, so you've discovered a time machine, but actually what happens is that you take energy away from the particles, so when they do collide, they don't collide with enough energy. What would happen to a reaction if the temperature was lowered? Would it go slower or faster?
Slower or faster? I seriously don't know.
So a reaction goes slower when the temperature is lowered.
Okay.
Because they've got less kinetic energy. That means they go slower, and when they collide, they haven't got enough energy to overcome the activation energy. Draw the effect the temperature has on the rate of reaction according to collision theory. Now what I will do here is kind of, you've got particles wandering around, they hit each other and they bounce off, okay? Bounce. But if you have a high temperature, as they come together, and then I'll do speed. they smash each other with enough temperature to overcome the activation energy, so you get a reaction occurring. Okay, I'm gonna really rush through this now. Basically, catalysts do something special. This is a normal reaction. We start, we end. This is an energy diagram. We're gonna go through these next half term. If you start here with your reactants and you've got your products here, this bit of energy is needed to start the reaction. So for example, this piece of paper, is it burning?
No.
How do I make it burn?
Match.
Match, light it, okay? If I was on the sun, would I need a match?
No.
Why?
Because it's so hot.
It's so hot already.
That all the paper will just turn into ashes immediately.
Paper won't exist on the sun, will it?
Yeah.
It'll be ash. So what you do, you're actually giving it activation energy. Now, if you had a catalyst lowers this activation energy. So you haven't got to give it as much energy. So if you use a catalyst on paper, perhaps you would get it to burn at normal temperature. I don't think there is such a thing, but there you go. And surface area. Now, surface area, basically, if you have a big sugar cube or if you have lots of small sugar cubes, which one dissolves faster? Small or big?
The small.
The small, you know, sugar powder, sugar cube. Sugar powder dissolves faster.
Yeah, because there's only there's one big particle when there could be like lots of little particles.
Yeah, so remember, when these are hitting, you cannot touch those particles on the inside. You cannot touch them. Okay? Sketch a graph to show our surface area. Well, you know, if we got something like a normal reaction here, that would be, say, the time taken for a sugar cube to dissolve. If you used powdered sugar, just normal sugar, the time taken, you know, would be a lot shorter. But again, if we're talking about product disappearing or mass, it will always be the same amount if you use the same amount at the start, just affecting the time getting there. So potatoes, they cook faster when they are cut into smaller pieces. Okay, concentration is very similar. All concentration means is that there's more particles all together. You know, if we've done half of these, bang it, compare that to low concentration. Just think about going down a busy street. There's more chance of you colliding someone than if you went on a quiet street. Like if you went out now into town, it's quiet because everyone's in their house. You're not going to bump into anyone.
Yeah, social distancing and everything.
Social distancing and everything. So statistically, you're going to bang in, and chances are you're going to have more collisions, therefore more reactions. And then.
So this is 2019, and this is 2020.
Yeah. Yes. Good one. And then, you know, if we're talking about concentration, this could be a low concentration. This could be a higher concentration. Okay. It's all according to how much stuff we got here, because if you've got a higher concentration, you could end up with a bit more products or reactants. You know, just as long as you know that the rate's increased in terms of the gradient.
Yep.
What would happen to the rate of reaction between magnesium and hydrochloric acid if the concentration of hydrochloric acid was double? Well, actually, it should go twice as fast. It should go twice as fast. And this takes us in nicely to AS. When we talk about rates in a bit more detail. I'm hoping everyone's going to be doing chemistry. So, that is me running through this very, very quickly. I say quickly, I think I've probably taken too long.
It has been 14 minutes.
40 minutes. I've got to watch this video back now and make sure that we're okay.
So 14 and 5, 46.
I've got to listen to me. Pause it for a minute, please, Anne. We back?
Yep.
And just before I leave, I just kind of get my dad joke book out. Why did the vampire leave Taylor Swift alone?
Why?
Because she had bad blood. Right.
Wait, what?
It's a song she sings, Bad Blood. No, I got bad. Right, anyway, right, let's stop there. Give me an email if you need any help. See you all soon.
Make sure to check out my channel.
Check out Emmett's channel as well.
Yeah, you